Good morning, all of you. Thank you for joining our webinar on the importance of material modeling and additive manufacturing. My name is Sarah Abdi, and I'm just going to get us started here. Today, we're going to discuss the importance of material modeling and additive manufacturing, as well as teach you all a little bit about why using AlphaSTAR's material modeling software, MCQ, can benefit users in the AM process. A little bit of background on AlphaSTAR Corporation. ASA is headquartered in Long Beach, California, and has been in business for 28 years, providing innovative physics-based simulation technologies and developing software tools for modeling and simulation of advanced composite materials and structures in the aerospace, automotive, defense, and energy industries worldwide. At the end of our presentation today, we'll have an opportunity for Q&A. So if any of you want to submit questions during the presentation, please do so on the WebEx screen. This way you don't lose your train of thought. Today, I will be introducing you to our presenter, Dr. Harsh Baid, one of the esteemed research scientists at AlphaSTAR. So without further ado, I'm going to pass it over to Harsh to get this presentation going.
Thank you, Sarah. Good morning, everyone. Thank you for attending this webinar. I'm on the slide number 4. I'm going to talk about the agenda for today's webinar, looking into the importance of material modeling in additive manufacturing. So we are going to look into the challenges in additive manufacturing in terms of material modeling, process modeling, and service load simulations. Since this webinar is focused more into material modeling, so I'm going to focus my webinar in material modeling challenges. Then I'm going to talk about why AlphaSTAR MCQ, which is Material Characterization Qualification Software for AM process. The software predicts mechanical fracture creep properties versus temperature. It also predicts material thermal process through thickness, looking into the heated affected zone, melting, solidification, and cooling process. Then I'm also going to go through a couple of case studies, one on AM polymer material modeling and another one on AM metal material modeling. I'm also going to go over a demo of the MCQ Chopped software looking into polymer material modeling of 3D printed ABS CF13 material. Then there'll be a conclusion, and towards the end of the webinar, we're also going to have a Q&A session. Moving into slide number 5, this slide talks about the challenges in AM thermoplastics. Usually thermal loading induces residual stresses and delaminations. As you can see on the top right, this is a printing process of an AM thermoplastic, and there's a thermography of printing shown here, the animation shown here on the right. So during this process, usually what happens is there are a lot of cracks within the beads are introduced. Also, there are issues inside the bead itself, between the fiber and the matrix. I'm going to look into these issues in more detail in my next slide. Slide number 6 talks about the challenges in multi-material AM process. So the material model should consider defects in as-built printed parts. That's the key here. And that defect needs to be addressed in the material modeling itself. On the left, you see the thermoplastic, which has high porosity issues. It has poly to filler interfacial bonding issues, residual stress issues, delamination, wrinkle issues, defects such as fiber waviness, agglomeration, and voids, and other issues. Looking into the picture on the bottom left, you can see there's an issue between the fiber and the matrix. There's an interfacial issue. And on the right-hand side, you see between the layers. When the printed layers, they have delamination issue, porosity issues, and all these type of anomalies that happens during the printing process. So these type of issues needs to be addressed within the material modeling. That's the goal of MCQ material modeling software is. On the right-hand side, you see the multifunctional material itself. We have issues with gas and process-induced porosity, unfused powder, dissimilar material. You have joining dissimilar material that introduces debonding, On the bottom left, on the right-hand side, you see the gas porosity issues right here, and on the right-hand side, you see the metal to PMC issues. So these are the key challenges that happens in multi-material AM process, and we need to address these key challenges in the material modeling itself. Slide number 7 talks about the challenges in AM metals. So definitely the part needs to be qualified and needs to be certified. So the key issues that we have, or the key challenges that we have in AM metals, are gas porous, unfused powder, we have balling issues, warping, delamination, and swelling. These introduces intergranular cracks, surface cracks, and then you end up with a good part, or a wrinkled part, or a cracked part. These are inherent defects resulting from AM process for metals. In general, the fabrication using conventional directed energy deposition technology introduces high residual stresses, surface roughnesses, voids and cracks, exhibits oxidation, inconsistent density, anisotropic microstructures, and mechanical behaviors such as static and fatigue. So all these challenges also in AM metals need to be addressed within the material modeling itself. So that's why the MCQ, AlphaSTAR MCQ material modeling tool becomes very efficient before we get into the simulation mode. Moving into slide number 8, GENOA 3DP, that's the AlphaSTAR in-house 3DP software, which follows the ICME, which is Integrated Computational Material Engineering Tool for AM process. For multi-scale modeling of metals, thermoplastics, thermosets, and ceramics. The philosophy that we follow in this process is we start with material calibration, verification, then we validate it, and then we predict. Since this webinar is mostly focused into material modeling, the philosophy that we're going to look into here in this flow process would be calibration of the material and then verification, validation of the material with available test. And as you can see, there is a flow process here. We start all the way from grain and grain boundary, take it to an homogenization approach, to fracture toughness, to fatigue crack, to all the way up to an hierarchy, heat like a structure, something like an heat exchanger. So that's the philosophy generally we follow in our ICME tool for AM process under the 3DP, GENOA 3DP software. Again, going from calibration, verification, validation, all the way to prediction process. And in this webinar, I'm going to focus into calibration and verification process. Looking into slide number 9 now, this is MCQ capabilities for additive manufacturing. First, we always start with an in-situ monitoring, which detects defects, voids, anomalies, and which eventually becomes input to the material modeling world. On the left, you see an example of an heated chamber end canal. You see an animation going on here, which shows the temperature profile of each and every printed layer. That's an heated chamber part. And on the right-hand side, once the part is built, we can calculate the residual stresses that builds in there. And the picture on the right-hand side shows the scanned camera defects delamination. So these are the defects that we can detect each layer by layer using a scan camera technology. And these defects becomes, or the anomalies becomes a direct input to the material modeling analysis. On the left-hand side, on the bottom left, you see the polymer material modeling. We have database for 3D printed polymer material modeling for ULTEM 1010, ABS, and others. We calculate the mechanical properties, predict the neat matrix with voids, with inclusions. We also calculate temperature-dependent material properties, both modulus and strength. We have lots of test-validated cases, for example, for wrinkling effect, for delaminations, and other types. People who are interested in metal powder material modeling, if you look at the bottom right, we also have database for N-canal 718, titanium, and PS steel. Again, we also calculate the material properties, stress strain curve, yield, elongation, ultimates. We also can predict temperature-dependent material properties, fracture toughness, crack growth, fatigue life prediction, phase changes, intergranular, transgranular void nucleation growth issues, also surface roughness predictions. We also consider environmental effects, and we can predict those kind of things, the oxidation and diffusional creep. We also have test-validated cases for residual stress calculations, voids, roughness, and others. So far in our agenda, we have talked about the challenges that we get in additive manufacturing process, especially in the material modeling world. Also, we look slightly into process modeling and service load issues. And also, we talked about why AlphaSTAR MCQ software, what are the capabilities, how we can resolve this issue using MCQ software. Now, I'm going to look into the predict material thermal process through thickness, especially into the heat-affected zones and the melting process. Slide number 11 goes to the validation of heat-affected zone and melting process. As you can see, the thermal process is affected by voids, shrinkage, conductivity, conduction, and radiation. On the upper part of this slide, you see the heat-affected zone calculated, actually predicted from the test itself, which is a thermal Weiss measure profile you can see on the upper left. On the middle, this is show that analytically we can calculate the heat-affected zone. It's in each and every step of the 3D printed process. On the right-hand side, you see the FEM of heat-affected zone shaped through the thickness. One of the key difference between the analytical and the numerical one is analytical takes seconds, whereas the numerical takes minutes to solve these issues. On the bottom, we're going to look into the melting through the thickness. There is a dynamic X-ray image shown on the bottom left of the melting through the thickness, and it's one of the regions here is magnified here, and you can see it shows the footprint of the dynamic of the melt pool, which shows about 150 microns. And on the right-hand side, we do the prediction using ULTEM algorithm, which also shows very close to the test available X-ray test, about 120 microns. And this also takes seconds to run the analysis. In slide number 12, I'm going to focus on the MCQ nano or chopped capabilities for AM of polymers. One more time, polymer material modeling, we have database for ULTEM 1010, ABS, and others. We can predict mechanical properties for the neat, with void, inclusion. We can predict temperature-dependent material properties, both modulus and strength, and we have lots of test-validated cases for different type of scenarios. For example, wrinkling and delamination. So the MCQ chopped capabilities, which is also independent of FEM, is shown in this chart. The typical input for an MCQ chopped software is the basic fiber and matrix properties. For example, density, modulus, strength, and also if you have nonlinearity in your matrix or each layer, you can also introduce that in the input. This can be also calculated from the MCQ software and can be put it back as an input. It could put it back as an input to the MCQ chopped. We also look into manufacturing defects such as fiber waviness, void shapes, agglomeration, and interface. So once the input is established, the fiber and matrix properties are established. The fiber particle shape, size, and aspect ratio for different type of particles, for example, disc, ellipsoidal, sphere, or cylindrical. Once these are all established, the MCQ chopped software can give us stiffnesses, strength, and also thermal and electrical properties. It also predicts the fiber orientation, or we call it tensor orientation, through the thickness, and it's also been validated by test. The MCQ chopped software also is capable of running a progressive analysis to produce the stress strain curve in different directions, for example, in the flow direction, the cross flow, shear, or any other orientation. It also performs material uncertainties, fatigue life, and design failure envelope. Again, one more time. In MCQ chopped software, the the typical input that goes in there is the basic fiber and matrix properties, geometry, is shape, aspect ratio, distribution, and size. Also the nonlinearity in the matrix or each layer, and manufacturing defects such as fiber waviness, void, agglomeration, and interface. Once all these are inputted in the MCQ Chopped software, it predicts the stiffness, the strength, and also the thermal and electrical properties, and also the orientation of the fiber through the thickness. Now I'm going to go over a case study using the MCQ Chopped software for an unfilled 3D printed ULTEM 1010 material. So the approach we take here is a Nano-Mechanics implementation with a cylindrical air particle for this particular case study. On the upper left, you see the matrix is an ULTEM 1010, and the inclusion is an air particle which is modeled as cylindrical voids. On the bottom left, that's what you see here. The cylindrical void has a weight ratio, volume ratio, the length, width, height, and these are modeled as cylindrical voids with 22% of air particle considered here. There's also applied stress strain curve, which is also part of the input of this software. The output that we get out of this MCQ Chopped software is a modulus in each and every direction, as well as the strength. And these were also test validated for multiple cases, for the tensile modulus, for tensile strength, and compressive strength. And as you can see here, the percent difference is very low, about 3 to 4% in the XZ direction, and the ZX direction is close to less than almost 10%. So that shows that the material calibration that we have done in our input for the MCQ Chopped is valuable and can be test validated. Another case study is a continuation of this ULTEM 3D printed ULTEM 1010 composite is now the filled. In the previous case study, we saw the unfilled. Now here's the filled. So we take the unfilled matrix properties here calibrated, and we fill it with carbon fibers here as a filler. As you can see, the properties are shown here for the carbon fiber, the modulus, and the strength. Same thing for the matrix properties here. At the bottom, you see the nonlinearity that is being introduced for both the filler and the matrix. The output of this analysis gives we performed a progressive failure here, and it gives the stress strain curve in 0 degrees, 90 degrees, and plus minus 45 degree oriented plies. And also is being test validated. We also predict temperature-dependent thermal property, temperature-dependent mechanical properties for 3D printed material as well. For example, for a 3DP ULTEM 1010, as you can see, we use a multi-factor technique to calculate the temperature-dependent modulus, Poisson's ratio, and strength and failure type. On the upper left, you see the temperature versus modulus. Then on the right side, you see the temperature versus Poisson's ratio, and on the bottom right, you see the stress strain curve generated using this multi-factor technique for different temperatures, for 70 degree, 200, 300, and 390 degree Fahrenheit. On the bottom left, you see a progressive failure analysis being performed for a given layup, a plus minus 45 degree layup for a 70 degree Fahrenheit temperature material properties, and the mode of failure shown here through the thickness is in-plane shear, and MDE, which is modified distortion energy, which triggers that, which in-plane shear triggers that MDE basically. Another case study for another type of 3D printed material is for AS-ABS, material properties and scatter for FDM process. We predict the strength, modulus, scatter, and also compare with test. The typical input that goes for this analysis is the AS4, which is the fiber properties, and ABS, which is the matrix properties, the basic modulus, Poisson's ratio, and strength usually provided in the literature or by the vendor. We also need the weight, the fiber weight fraction. And this was a case study performed for a need for a test article with 10% weight ratio of the fiber, for 20%, 30%, and also 40%. For each fiber weight fraction, we had a fiber length defined. We also introduced void volume fraction for each cases. As you can see in the picture on the bottom left here, that as you go from left to right, how the void content changes. We also introduced interfacial strength parameter in our analysis. There was also second order orientation tensor for component provided for this particular material. So we also implemented that information into our material modeling. And at the end, we also performed probabilistic analysis with fiber length as a random variable. So given these inputs, the output that we get out of this thing, as shown here compared with test, is a tensile modulus and the tensile strength at each weight fraction of the fiber from 10 to 20 to 30 to 40, and also the scatter that we calculated using the probabilistic analysis for each case, both for the modulus and for the strength. And you can see that for the modulus, as the weight fraction of the fiber increases, it almost becomes like a plateau here. It saturates. Similar thing is also observed for the tensile strength as well. It increases. All of a sudden, there is a decrease in the slope here. So that clearly shows that increasing the weight fraction of the fiber does not really help to increase the modulus of the strength. It can also sometimes decrease it. So there is a saturation point, and that's been clearly modeled using MCQ Chopped software and has been very validated with test. Next, in slide number 18, I'm going to talk about MCQ capabilities for additive manufacturing of metal powders. One more time, the metal powder material modeling, the database we have is for Inconel 718, titanium, and PS steel. We calculate material properties, stress, strain curve, yield, elongation, and ultimates. We also calculate temperature-dependent material properties, fracture toughness, crack growth, fatigue life prediction. We look into the phase changes. We also calculate intergranular, transgranular void nucleation growth, surface toughness predictions, and also we consider environmental effects such as oxidation, diffusional creep. Also, we have test-validated cases for residual stress, voids, and roughnesses. In this slide, I'm showing the predict defects observed in AM process. For the local model, we look into the crack initiation and crack and growth predictions. On the upper left, you see the deviating cracks, the transgranular crack, and the intergranular crack. This is what we can predict using our AM process software. On the bottom, you see the void initiation and propagation. We can predict the surface roughness, and here's an example of the surface roughness predicted and compared with the bottom right test. On the next slide, which is slide 20, we also look into void formation and oxidation. We perform thermostructural plus damage computation analysis to predict the void content and oxidation. On the left, you see the global model, and we take the global model and we break it down to a bunch of local models. As you can see, the CPU times for the analysis for the global can take 36 hours, whereas the local, if you have a bunch of computers available, you can run them for only 1 hour and you can get the quick solution right away. And what it provides you is a void for each and every element, and also the oxidation for each and every element. So this becomes a very valuable information in our material modeling analysis. Okay, another case study that I'm going to show you for the metal AM process, the 3D printing stress strain curve prediction versus test for titanium aluminum alloy. So we use a direct metal laser sintering material, which is, and then we use a nano-based inclusion defect algorithm to predict the stress strain curves with and without the inclusion. For example, on the left-hand side, you see the titanium aluminum alloy material properties with air as inclusion, model as cylinders, and also we introduce the stress strain curve of the basic titanium aluminum alloy. On the right, the output that we get is modulus, strength, and longitudinal stress strain curve, and it's been compared with test. For the rod case, which is the red curve right here, for the rod with air particles, and the given as-built length stress strain curve. And it shows a pretty good comparison between the route with air particles and the as-built lengths. That shows that there were anomalies, which were inclusion as air particles, which were introduced inside the titanium aluminum to give us the correct stress strain curve, which can be easily compared with test. In the next slide, we continue with that same material, and we're going to perform 3D printing for fatigue prediction versus test. This is a validation of titanium aluminum again for DMLS at room temperature. We start with a full stress strain curve. We look into the material properties and the geometry of the material. We calculate the toughness versus thickness, and then we run the FCG, which is FCG to calculate the delta dA over dN curve as shown in the picture right here. So all this process is done using MCQ Metal software. Once this curve is available, we can take this information inside an actual FEM coupon simulation here, and we can predict the SN curve here as shown in the bottom right for R equal to 0.1 case here. And the triangle ones are predicted using GENOA, which is a simulation, and the circle ones are given from test, and it shows a pretty good comparison right here. So the correlation between the AM material output and models are clearly shown here. Now I'm going to give you a demo of the MCQ Chopped software. When you launch the MCQ Chopped software, there is a welcome page right here which talks about the material characterization, qualification, chart fiber. There's a quick start navigation option here. It goes through the navigation of all the key tools here available in the MCQ Chopped. You can go back and then you can click on the step-by-step tutorials that are available. For example, in this software, we have two detailed step-by-step tutorials available, and one of them is for the 3D printed material, which is AS-ABS. And then you can go back to the home screen, and also you can click on the test validations. We have a bunch of test validation cases available. Altogether, we have 22 of them which have been validated, and these are the case studies for MCQ Chopped software. Okay, now I'm going to, and also you can see in the tree on the left-hand side, there's a tutorial, all this solution which was showing on the right side anyways, and also you have test validated all these different cases right here. I'm going to bring up one of those examples. For example, I'm going to look into 3D printing material, which is AS-ABS. Open this project. And all of these case studies and the tutorials comes with the detailed documentation. For example, for this particular case, we have a step-by-step. It goes through each and step. What are the inputs? What are the assumptions? What are the outputs? And if test data is available compared with test. It goes through the entire step-by-step process of this particular tutorial. And the typical input for this one is the AS4 material, as you can see on the left side here, and also the porous ABS material. If I click on the chopped composite, this shows the input that requires for the particle itself, the weight fraction, volume ratio, length, and diameter of the particle. In this case, we're assuming particle to be fiber, which is cylinder. And you can also make it either straight or wavy, and there are lots of other parameters available. For example, you have option to put more voids in your material. You can enable interface. You can have a uniform dispersion, or you can have a non-uniform dispersion. And if I look into the analysis tool, we have a bunch of analysis available. One of the key analysis is chopped mechanics. I'm going to run this analysis. And while this is running, I'm going to talk about other analysis tools available here. One of them is orientation distribution determination, chop characterization, material nonlinearity calculation, aligned nonlinearity, progressive failure analysis, design failure envelopes, and material uncertainties. So while this is running, it takes about a few seconds to run the chopped mechanics analysis, and pretty soon I'm going to show you what the outputs are. So you can always go back to the notes and go through the tutorial in detail. You can always print this out, go through it, and practice this thing. It's a very user-friendly tool, and you can quickly learn this software. I would say in hours. You can go through this tutorial step by step, and in no time you can become a professional in this software. Okay, so once this analysis is complete, you can see the output here. The modulus, Poisson's ratio, and strength are the key mechanical properties that are being calculated using this chopped mechanics analysis for aligned, when all the fibers align in one direction, for 2D random, 3D random, and user defined. So if you have a layer through the thickness and you have orientation of fiber, you can also look into all those, and you can see here the modulus changes when you go look into the different alignment of the particle. Also strength, Poisson's ratio, same thing, you can for different categories, and also for the modulus. There's another key analysis tool here, which is called orientation tensor determination. And the setup for that thing looks kind of right here. So you define the thickness, and you can input the orientation tensor component through the thickness of the given material, either from the test or from other software such as MoldX 3D or MoldFlow. And once you run this analysis, what it gives you what type of orientation of the fiber you have through the thickness. For example, here when I run this analysis, it tells you that's the orientation of the fiber is through the thickness. It's 0 plus minus 45 orientation of the fiber through the thickness. I can export this orientation back to my input. And when I click on this orientation distribution here, you can clearly see that the thickness of it, how many layers are there, and these are the orientation through the thickness and thickness of each and every layer. And I can rerun the chopped mechanics, and it will provide me the information of not only for the line for 2D or 3D, but also the properties for the orientation for the entire test specimen with that oriented fibers. Okay, so that's the basic of this software. I'm going to switch back to the presentation while this is running. And in conclusion, I'm going to talk about the importance. We started with importance of material modeling in AM process. And what we proved here, the MCQ material modeling software provides validated material properties for both polymer and metals AM material. For the polymers, if we look into more detail, we characterize the material with limited coupon test, with inclusion, orientation, with different aspect ratio of the fiber, for example, length and diameter. We can calculate the residual stresses, deformation, delamination, initiation at different locations, and also fracture propagation. And also we looked into the contribution of failure types through the thickness and the location of damage and fracture. For metal powder, we looked into the diffusional creep, for example, void, surface roughness predictions. We also calculated the stress strain curves, and also we looked into the fatigue plus defects, and we showed you the AN and SN curves. I'm going to hand the presentation back to Sarah, and she's going to conclude it.
Thank you, Dr. Baid, for the presentation. I think that we can go ahead and get right into our Q&A. We did have some questions that already came in, but if any of you have any questions as we go through these, please raise your hand. The first question that we had come through, is the software capable of calculating temperature-dependent properties?
Yes, definitely. In one of the slides, we did show we have a multi-factor technique to calculate the temperature of the to calculate the material property with respect to temperature. As you can see here, we showed an example for a field 3D printed ULTEM 1010 material.
And let's see here. We had a couple other questions that just came through. Yes, you guys will be able to get a copy of the presentation at the end. Let's see. For metal AM, how does your software interact with the laser source? If at all, examples, the ability to control laser spot, beam shaping, or scanning.
Let's see, I can do this. Okay, my name is Cody Godinez. I'm going to jump in on this question from AlphaSTAR. So currently, we're working on hooking up the feedback control to the laser source. That's one of the works in progress. It's a future thing for us, but it's on our spotlight. So we can take in the information real time and then give solutions, but we need to finish that final link of the feedback to the laser source right now. So currently, as the laser is being moved, we can go and inspect the surface defects, surface roughness, do thermal and structural predictions, but again, that last link needs to be complete.
One more question. How do you take the output of MCQ to an actual FEM analysis?
Going back to the same slide here, as you can see, the MCQ, once the material properties are calibrated, you can take these material properties as either a direct input as a native material for different FEM softwares, or you can also take it as a user-defined material card, which can be easily controlled by GENOA in the background to run the analysis for most of the FEM available FEM softwares.
Okay, perfect. Let's see if we have any additional questions here. Okay, I think we have one additional question, and then I'll give another minute for anyone else that might have something. But in the meantime, after we answer this question, I'm going to push a poll through to you guys, just a couple questions. If you can please take a moment to answer. Do we need another software to be able to use MCQ?
No, MCQ is by itself is a standalone software. You do all your material modeling and characterize it, calibrate it, validate it, and once you have the material property established, as I said before, you can take this either as a native material to your FE solver, or you can take it as a user-defined material card in your FE solver.
All right, so any last-minute questions? While we wait, I'm going to push these polls through to you guys. You can just take a minute to answer for us. And one last question. So any last questions? I think that's all we have. So I wanted to thank all of you for attending today. If you have any additional questions for our team or would like more information, please reach out via the email on the screen. And other than that, thank you all, and I hope you have a happy rest of your Thursday.